Okay.
Okay.
Right. It's a great pleasure of Yinan Wang from Peking University. And he talk about continuous categorical symmetries and anomalies. Take it away.
Yeah, thank you, Sakura. Going to first thank the organizers, especially Sakura, for inviting me to give a online talk here about our recent series of works, starting from last year, on how to incorporate continuous Lie group symmetries like U1 or SU2 in the modern framework of generalized global symmetries, in particular, same TFTs, group homology, and category theories, and so on, which has been a relatively less understood and a very now a pretty popular topic in the field now. So I'm first going to briefly introduce the framework, the setup. So I'm only going to, for simplicity, I'm only going to talk about two-dimensional physical system living on a 2D manifold, and the symmetry group is just a zero-form symmetry group. So no higher form symmetries. So I'm first going to reveal the basics everybody knows about the finite group G symmetries. And in this case, you have two equivalent descriptions for the symmetry generators. The first one is the topological defect lines, or in general, a topological defect networks that are, consist of these UG U operators, that's called dimension one, living in the 2D space-time, which are labeled by group elements, say little g, little h, and little gh, and they satisfy the Euro group fusion rule and can be combined into this topological defect network. So this for finite group G, this TDN also have an equivalent description of a set of flat background gauge field A taking value in the group G with a group value gauge field in the case of finite G. Basically, you can basically cut this region, cut the whole 2D space-time into three regions that are labeled by I, J, and K. And living on the edge, there is a gauge field called Aij, AJK, or AIK, whose value, for instance, the Aij is just exactly equal to the group element little g. That is, the one labeled by the UG that's perpendicular to the IJ edge. And so the effect of either the TDN or the flat background gauge field is that if you move some charged operators phi charged under the global symmetry group G, say from J to I, then this phi charged operator will be acted by the group element little g, so phi becomes little g dot phi. Equivalently, you can also say that it's acted by the value of this holonomy Aij, or the value of this gauge field over here along this edge, so it also becomes Aij dot phi, because after all, Aij and little g are the same thing, just the same group elements. So you can see that the group fusion rule of the group G is translated to the flatness condition of your flat background gauge field, J times AJK equal to AIK. And in other words, really for the finite group G here, the uh, the gauge field A living on the edge should be interpreted as something like a holonomy that e to the algebra element if you want to have an analogous picture for the continuous group later. So this is a basic thing for finite group G that we all know, finite global symmetries. And then what about the gauging the finite global symmetries? The gauging means that in the partition function, we are summing up all the TDN configurations inserted in the space-time in the path integral. That will be equivalent to summing over all the configurations of flat gauge fields that are coupled to a system, and the partition function become a generating functional that encoding the coupling between the gauge field to a physical system. And for the case of the finite G, the gauge field here summing over are all the flat gauge field modeled out the gauge transformation, and these equivalent classes are characterized by the holonomy on trivial holonomy around one cycles. And more precisely speaking, these are equal to the home from the fundamental group of a space-time manifold to the group G modeled out by the adjoint action of G. And then for the new gauge system, the partition function will be equal to just a summing over, you just sum over the generating functional after you insert different a's. And also, you could also introduce some phase factor in each term that are related to the background gauge field for a dual symmetry. which I'll be talking about later in the next page. And after you gauge a finite group G, because the gauge field you introduce is always flat, this will generate the dual symmetry that are labeled by element in the rep G, labeled by representation of G. The reason is very simple. It's because the dual rep G or G hat symmetry is generated by the Wilson loop operators that are labeled by some representation. The subgroup is a representation of your original group G. And because in the case of a finite G, the gauge fields are always flat. So the Wilson loop operator you construct in this way is always topological, and the topological operator will generate a new symmetry that are labeled by representation R over here. For example, when G is equal to Zn, after you gauge it, there will be a dual G hat, and also another Zn symmetry, because, well, for the abelian case, G hat is just a Pontryagin dual of your Zn, and the second Gn just one-to-one correspond to the irreducible representation, unitary representation of the Zn group G over here. Okay. And moreover, when G is a finite non-abelian group, the dual rep G symmetry will be non-invertible representation symmetry. And each element in the rep G symmetry will obey the general fusion rule of representations, just a tensor product decomposition of a different E-reps instead of a group multiplication. Okay. And also, of course, in many cases, there's some obstruction to gauging a finite group symmetry, finite G symmetry. And you call this obstruction a tooth anomaly. This basically means that after the gauging, the new quantum partition function is no longer gauge invariant, i.e., after a gauge transformation of this newly introduced gauge field, there will be a non-trivial U1 phase factor in front of the ZA, and which cannot be cancelled by a local gauge transformation. And in many cases, this phase factor can also be cancelled if you couple your d-dimensional system, the boundary system, to a one-dimensional higher bulk TQFT. And with a properly chosen Lagrangian topological action for the bulk TQFT, the whole system can be gauge invariant. This is called decent formalism or anomaly inflow, or for the case of, in the high energy community, and is also known as SPG phase in the larger condensed matter literature. Okay. Then let's consider the case of a finite group G, a zero-form symmetry, a finite group G in two-dimensional space-time. It's also known that the anomaly of this finite group G is correspond to the breaking of a associativity law in the two different kinds of insertion of total defect networks that are related by the so-called F move. Here there are two pictures which will combine three different three-group elements, G1, G2, and G3 in two different ways. And because its order of composition is different, there could be a non-trivial U1 phase factor from the left to the right. And when there does not exist a local U1 function, the U1 valued function f from G times G to U1 that cancels this omega term, we will say that there's an anomaly, tooth anomaly, engaging the global symmetry G. In that case, the omega is also correspond to an element of the third group homology of G taking value in U1. So this is some very well-known stuff, especially in condensed matter literature. And these are all all things that reveal about the finite group symmetry that everybody should know. Now the question is, what about the continuous symmetry G? So can we employ all the toolkits that I introduced before and apply them to the Lie groups? Then for the case of continuous G, you have to be very careful about there are actually two different kinds of gauging that are fundamentally different. So the first one is a Euro type of gauging, like how do we achieve the QED or QCD by gauging a global symmetry in a free system. And then in this case, we are gauging with a dynamical gauge field with a non-trivial dynamical degree freedoms. which is also non-flat. It's not a flat gauge field. But after the gauging, there will be a rich new local dynamics associated to either photon or gluon, and the whole theory is completely different. But today I'm going to emphasize that in order to use the TDN or dual symmetry or anything like SymTFT or everything that I'm going to introduce later, you have to be using the second type of gauging, which is the gauging with a flat gauge field, or in short, the flat gauging. So what do we mean by flat gauging? As I will show in example, the flat gauging doesn't mean that you just have a f equals 0 at every point in the space-time. The more precise definition is that if you evaluate the holonomy, the group value holonomy around the topological trivial loop in your space-time, then this holonomy should be trivial, equal to a trivial element in your group G. So this is actually a weaker condition for the flat gauge field, and it's exactly equivalent to the definition of flat gauge field for the finite group case, right? But we are defining this using the exponential over A with the holonomy. And only by imposing flatness condition, we can use a topological defect network picture, because as you can see here, the group theory log says G times H equal to GH. So this only have a dual holonomy picture if you are using a flat gauge field. Otherwise, even this TGN will not work here. And also, if you want to have a dual symmetry after gauging the continuous group G, only with a flat gauge field, the Wilson loops are topological. In contrast, if you are working in QD or QCD, it's just obvious that in QD and QCD, the Wilson loop are all non-topological. So that cannot generate your dual symmetry RepG. And only when we couple a flat gauge field with your system, you can have a dual RepG global symmetry. Okay.
Can I ask a question? Do you make any assumption about G being a compact Lie group or no?
Yeah. For the purpose of this talk, I'm going to be restricted to compact Lie groups. Yeah.
Okay.
But it's just that well, you can also talk about R group like R. It's just that there's no unitary faithful representation. Yeah, only problem is that. So
Sorry,
for yeah,
I have
yeah.
another question. Maybe it's more a comment, but you're saying that C must be topologically trivial, but sometimes might be that C is topologically trivial in space-time, but it's not in space-time with insert or removed.
Yeah.
For instance, if you insert a twist defect,
Yeah,
then the
exactly.
Wilson line should be able to
Yeah,
measure the charge.
yes. Yeah, it's like what you're saying is more correct understanding of this topological trivialness. Yeah, because there could be so I think no, actually, wait, I think yeah, I really just mean topological trivial. See,
But
because
then you're not allowing intersection of twist defects.
yeah, sure, yeah. If I have more exactly thing like that, you could have a non-trivial holonomy around it. Yeah, sure.
Uh-huh.
But this is almost similar as just digging a hole in your space-time.
Yes, indeed.
Yeah, you have a non-trivial
Thanks.
holonomy around it. Sure, yeah.
Yeah.
Yeah, so I think yeah. So thanks for coming. It's a more precise way of saying that. Yeah. Okay, and after clarifying this point, I'm going to present this recent work on, you know, uh, uh, so we have a question on the anomaly for continuous symmetry, basically. So the question
Sorry,
is just
can I just
pretty
ask a
yeah
question?
yeah.
So do you make a distinction between continuous and smooth symmetries
Sorry, was a continuous what symmetry?
versus smooth symmetries? I mean, sometimes you
Uh,
have
s-
actions that are
oh,
continuous but not smooth, right?
okay, you mean Q mod Z versus U1, right? Yeah. Did you mean the Q mod Z issue?
I mean, not necessarily, but yeah, I mean, sometimes yeah, I mean, that's just, I suppose, like a general observation, right? That sometimes you have actions that are continuous but are not differentiable. So Do we see this difference here?
So yeah, what I mean here is a Lie group is of course a differentiable. It's a right, and yeah, there are difference. You'll say this in the next slide. Yes, yeah, good question. Yeah, but the difference is yeah, I'll mention that later. Yeah, thanks. Okay, so our first physical question is that we know that for continuous symmetry group like U1 or SU2, then the anomalies are just described by anomaly polynomials. Like they are gauge invariant anomaly polynomial that f at f, or the three-form anomaly polynomial that a at f, right? Then for the finite group, we also know that the finite group, in finite group case, the anomaly is described by the surgical cohomology, and which is physically described by the f move. Then can we unify this the Lie group also in that picture? It's a very natural question. And our answer is yes, but there are some details and subtleties in it. The basic the problem, I think many people had asked or wondering about this question before. So the basic problem or the issue here is that we have to be careful about the group cohomology, because you know, for instance, for the Lie groups, we know that anomaly polynomial FHF, these are Chern classes, second Chern class, and there are generators of this H4BGZ group. For instance, when G is U1 or SU2, this H4BGZ just equal to Z, and the generator is precisely this FHF or trace FHF for SU2. And then, well, so this works, this is equal to H3BGU1. However, in general, if G is not finite, then H3BGU1 is not the same as the third group homology, GU1. So, you know, when you really talk about the Lie group, group homology and the BGZ thing for Lie group, you have to be extra careful about what you are really defining, because you cannot naively using these relations as what you are accustomed with in the finite group case. So then, what can we do, right? So, you know, we have the H3BGU, and this is totally fine. But what about the H3 group GU1? So this is a kind of, so how can we introduce a well-defined notion for search cohomology that incorporates FHF generators? Then in the next slide. So our answer is that we have to use the discrete topology. That is, we are defining a circle homology for this discrete space called the G delta, where G can be the Lie group like a U1, but we just pretend that it's just a set. You know, it has a trivial topology in the sense every subset is an open set in this G delta. And then also the representative of the circle cohomology is not required to be continuous. It just can be a general discontinuous function. Right. And then, so, but where does FHF live? Where does H4BGZ live? So, at least this H4BGZ will be an injective subgroup. It is an injection from the H4BGZ to this H3 of G delta. And it's just it's a subgroup of that. So, you know, basically the physical conclusion is that although FHS is maybe not everything in that very highly complicated circle homology, but it's still a faithful object. You know, you can still talk about the Z subgroup living in the large group like this. Okay, so now this mathematically a little bit more technical. Let's consider K of G equal to U1. And you know, everybody knows you can think about U1 as a limit of Zn when goes to infinity. However, you have to be careful about that, because I think for most of people in the condensed matter community, they're not careful enough in this point. So what you want to do here to get a proper direct limit when n goes to infinity is actually the direct limit of Zn. And that will equal to Q mod Z. As I think that's Alonso asked this question just before. So this Q mod Z is a non-differentiable but still continuous symmetry group, as you see here. But the U1 as a space is not just a Q mod Z, because, you know, apart from the rational numbers, you also have irrational numbers. And that is, roughly speaking, you can think about the U1 delta as a direct sum of an infinite dimensional vector space of a Q mod Z with this very complicated group called a very exotic group called R mod Q. So for the Q mod Z part, you know that from also you can review from the Pavel Putrov nice paper on the Q mod Z symmetry, the circle cohomology for Q mod Z equal to Z hat the profinite integers, which is the completion for the is the intergroup Z that containing all the Zn as the proper subgroups. And also using Kuhn's formula, we know that this very highly complicated object such as H3 U1 delta U1 is roughly speaking equal to profinite integers plus a very complicated thing that I don't want to comment here. However, we still have a natural injection of this FHF part, this is a Z injection Z into the profinite integer Z hat, and this is a perfectly injection. Okay.
Sorry, can you clarify in which sense do you regard Q mod Z as being a continuous group?
Yeah. So, well, you know what? This is just like a mathematical terminology, I think. So, yeah, some people think will define the Q mod Z as a continuous space, in contrast to a discrete space, because it's not discrete space. Discrete space means that every point has a finite distance between, from another point, right? So in that sense, Q mod Z is a continuous space. But I think for many people in this community, they may think Q mod Z is just a discrete group. Yeah. So it's a terminology anyway. Yeah.
Well, yes, because
But I think for the last question, he Alonso may think Q mod Z is a continuous group. Yeah. I don't know.
I think mathematically the point is that if you want to insist in having a Hausdorff topology, then you need to endow Q mod Z with discrete topology. If you're happy with non-Hausdorff topology, then you can use the topology as like embedded in U1.
Right. Yeah. I'm not going to. Yeah. I'm not really interested in this terminology. Yeah, issue here.
Okay, thanks.
Yeah. Okay. Okay. Yeah. Then our physical question, that was a technical, highly technical math part. The physical question is also very clear. It's just that we know that the anomaly for continuous group like U1 or SU2 should be described by anomaly polynomial. Then can we use a rearrangement of topological defect network to just derive this omega, to derive this representative for a U1 group, that correspond to our FHF anomaly polynomial, which we are interested in. And then what you can do is very clear. We just first have to introduce a flat gauge field associated to a TDL L labeled by group element into the L alpha, which is just a G group element. And picture it as follows. You have a TDL in the vertical direction, and so what does it do is that if you move a charge operator from left to the right, no matter how you move it from left to the right, it has to be acted by the same group element, that e to the I alpha. Then how do we introduce a dual gauge field to realize this is by introducing this discontinuous gauge field that proportional to the delta function. Only by defining this, you can you can fulfill your condition that no matter how you integrate from this point on the left to this point on the right, you get the same answer, just group element. And then with this flat gauge field, discontinuous flat gauge field, we can compute A and F correspond to any TDN even with fusion. And then realize the rearrangement of TDN the F move at a finite gauge transformation that will be acting on the physical anomaly polynomial. But for the details, it actually you have a different story for the U1 group and SU2 groups. The first one is the U1 group. We all know that the three-form anomaly polynomial is just this abelian Chern-Simons term. And after gauge transformation, A goes to A plus d epsilon. Zero, it differs by total derivative in 3D, but with the boundary induce a term, the epsilon dA on the 2D boundary. And then, you have a confusion that people asked before. So because we're all working in the case of a flat gauging, the A has to be flat. And now usually A is flat is equivalent to the fact that dA equals 0, as a vanishing field strength. But if really dA equals 0, then how can we have any anomaly if dA just vanishes? So the issue is just that lies in the definition I'm talking about before. So the flatness of A just means that if you integrate around the topology trivial loop, you have a trivial holonomy. And that's a weaker condition than D equals 0, as I will show you later. Okay. Now let's analyze this case of a junction of a 3-junction TDLs. And each piece is labeled by a group element e to the I alpha, where alpha takes value from 0 to 2 pi for the U1 case. And the key point is that if you take product of these two group elements is equal to e to the I, the square bracket alpha 1 plus alpha 2, the square bracket means mod 2 pi. It's just restricting alpha to taking value from 0 to 2 pi. And then, seeing that after you write down the dual gauge field, you could have a non-trivial field strength that's a proportional delta function that's localized at the junction point. And this is basically a winding number effect due to the fact that the U1 is not simply connected. Yeah. And in the other word, even with flat gauging, we can still have a non-zero F that's just only localized at the junction point. And that's the source of your anomaly, yeah, for the flat gauge. So with that in mind, we can also compute the dual flat gauge field that's corresponding to this more complicated configuration before and after the F move. And you realize that as a finite gauge transformation of your gauge field A, and you integrate this epsilon gauge transformation parameter times dA over your two-dimensional plane. And by that, we successfully compute the phase factor omega, and that's exactly given by this equation. And these are representative of the third group homology of U1 delta that I introduced before. And if you're familiar with the representative also for the H3 of Cn, you can see that this is perfectly consistent with the n goes to infinity limit of the Cn case. It's also speculated by Kawagoe and Mike Levin a few years ago, although I think they just take this infinity limit, and we provide the first and honest field theory derivation of this phase factor for the U1 case. Okay. And another comment is that you see that this function is not a continuous function because this one is like a step function. It's drastically different if alpha 2 plus alpha 3 exceeds 2 pi or not. Yeah. And that's consistent with the claim before that we have to use the discrete topology in defining the group homology for U1. It's all consistent. Okay. So that was for the U1. And then what about SU2 case? It's actually you have a pretty drastically different story. When the group is G like SU2 is simply connected, then there's no such winding number issue. And in principle, you can always smear out the TDN to get a vanishing field strength F equals 0 everywhere. But then you ask, where does the anomaly come from? But now for the non-abelian case, the three-form anomaly polynomial is just a non-abelian Chern-Simons form. And you see, even if you assign F equals 0, you still get this trace A wedge A term that is non-vanishing. So this is totally fine. And so to analyze this question fit more clearly in the geometric picture, we just put the TDN before after the F move on two different slices in the 3D space-time, box space-time, in the front and also in the back. And we are connecting the TDLs corresponding to the same group elements, say G1, G2, G3, and so on. So this picture, if you stare at it more carefully, that can be deformed to this tetrahedron picture, and where each edge is assigned with a different group element here. And so physically, what can you do? Is that before and after F move, you have two different flat gauge field configuration. And you can define an interpolating A that's living in the 3D bulk. Interpolating A before and after the F move, you get a flat gauge field A also in the 3D bulk. Because it's flat, locally we can write it as like some G tilde minus 1 times G tilde I on each patch, where G tilde is a map from the patch 3D space-time, from the 3D space-time to your group G. And after we integrate this I3, this cubic term in the 3D bulk, that can be pulled back to an integration actually on your group, on the Lie group G. And this one is exactly just a generator for the third theorem cohomology of G, taking value in Z. So here the omega-3 is a left invariant 3 form defined on the simple Lie group SU2.
Sorry, can I ask a question
yeah,
here?
yeah,
So
yeah.
for the cohomology computations, you're endowing G with the discrete topology.
Yeah.
But so here it seems like you're using a different topology to define the G tilde. Is that the case?
Yeah, so here is a I mean, I'm not doing anything. Yeah, yeah, I think so. Um, let me think. So you're asking whether the little g is differentiable, right?
Yeah. So for example, when you're writing right AI, right? So you have a DG tilde there,
Mm.
but then for the cohomology computations, you're working with the discrete topology on G. So I'm a little bit confused about
Yeah,
how
yeah,
these two
yes.
things work.
So
Yeah.
I think so here is just that I think honestly speaking, you should be you may be able to get a smooth G tilde here if you only when you somehow smear out the topology defect network. If you don't do that, it is still could be just a non-smooth function. Yeah.
Question?
But
Okay.
yeah,
Thank you.
yes.
Sorry, yeah, I had a question. So do I understand correctly, like that these the topological defect networks that you consider,
Yeah.
they only correspond to topologically trivial bundles? So the churn class is always trivial, even though there's DAs need not be zero.
Oh, yeah, that's also a good question. It's like um, also I think this ultimately lie in the question that when you say you're gauging the group G, you do you want to sum over all the topologically different bundles, right? I think that is the question, and then I think the short answer is yes.
But are those captured by defect networks in the sense that you're describing?
Mm, I think.
Maybe I have a comment on this. When you take a flat U1 bundle, doesn't mean that the first class is trivial, because the first class become equal to the Bockenstein of the gauge field. So it becomes a
Right.
torsion element. So you can detect it, but not on manifold without torsion. If you have a manifold with torsion, you can insert a defect network in which you can detect a non-trivial first class.
I see.
Yeah, I
And this
think
Bockstein is roughly like what Yinan was describing at the junction of three defects, right?
Yeah, probably yes.
But on any torsion-free two cycle, there's no non-trivial bundle.
Yeah, exactly.
Okay.
Hmm.
I had one more question actually. So it seems naively that this group cohomology looks a lot like that for Zn, right? This type 1 3-core cycle for Zn, with it appropriately taking the
Yeah,
large n
this
limit.
case, yeah, sure. Yeah, just like that.
But we know that, for instance, Zn to this power 3, for instance, has cocycles that
Yeah,
don't
of
reduce
course,
to U1
no.
cocycles.
Don't reduce to U1
Yeah.
cocycles at all. So
So you can't get, the converse thing would be that if you start with Un to the k and break down to Zn, you won't get all three cocycles. Notably, the type 3 cocycle cannot be obtained like this. So does this also match with some computation that you do
so
for?
okay, you mean these ones are not also not just equal to the mixed anomaly. So you have three copies of the okay. So and okay, and it also doesn't correspond to say A cup B cup C.
Yeah, it look like A cup B cup C.
Yeah, then it's A cup B
Z.
cup C, right?
And that's a U1 3 cocycle. I thought
Wait. I'm just asking, is it correspond to the, you have a Zn value gauge field, let's say, like ABC, then does it correspond to A cup B cup C?
yes.
Then I think, that case just also correspond to the, if you rewrite it using U1 value gauge field, which is also A cup A wedge B wedge C, right? It's no problem in that. Yeah, sure, but it's not the A wedge DA type. It's not this A wedge DA. Yeah, sure. It's not the same as that. But A wedge B wedge C. So
Okay. Yeah. Thanks.
right. Yeah, you can. Yeah, that's your question. But I think you can do the similar derivation here and try to find it. Yeah,
I see.
it's just not in this type. Yeah.
Thanks.
Okay. So here, yeah, I think, roughly speaking, so this is not anything that it's not super strange here. It's just for the SU2 case, it's a Euro stereo Wetzel Witten term, or the original Diagram Witten story in the 90s. So it's not super surprising, but it's just new. We just incorporate in this new F move language. Okay, right. So that was the anomaly for continuous symmetry part, and the next part will be a SymTFT for continuous symmetries. It's a very, I think all the audience here are experts, so I don't want to spend too much time on the basic of SymTFTs. It's basically, you have the slab and the topological boundary, dynamical boundary on its side. And before assigning appropriate boundary conditions, we just get a relative QFTs with only partition vectors. And only after choosing proper boundary conditions, we can get an absolute theory. And for instance, for the 2D system, on the side, same TFT will be 2 plus 1D TQFT. For instance, for the Zn zero form symmetry, we have a Lagrangian formulation of the same TFT using Zn valued the algebra value gauge fields. Like this is a BF term with another twist term that encoding the two anomaly, which is exactly obstructional gauging as I mentioned before. And then in this TQFT action, in absence of anomaly, has the following UG and VG hat topological anion lines that are integration of either the A hat gauge field or A gauge field, and they have this topological linking cohesion function like that. Okay. And in order to have a well-defined gauge invariant system with a bulk and a boundary, you have to impose proper topological boundary conditions. For instance, we can give a Dirichlet boundary condition to the A gauge field and the VG hat operators, which means that the little a will become the fixed background gauge field for the Zn zero form symmetry. And on the other hand, the UG operator will be having the Newman boundary condition. They can be freely put from the bulk to the boundary, and they are also corresponding to the topological operator that generate the Zn zero form symmetry after we collapse the slab to the slice, to the 2D physical system. And the charged operator OG hat, in the bulk picture, will be the one that end on the Wilson lines which hat, which are can be shrinked or condensed into nothing after the shrinking. And then, we also know that the gauging of a finite symmetry, like a Cn finite symmetry, is equivalent to changing topological boundary conditions. And in general, the set of the allowed topological boundary conditions are corresponding to giving discrete boundary condition to a subset of topological operators in the same TFT with a mutually trivial linking pairing. And in condensed matter language, this means you just choose to condense a subset of anyons. Okay. These are basics for the same TFT of finite symmetries. We also, besides the TQFT action description, we also have categorical, have another very nicely developed categorical language in the past few decades, maybe 10 years. And for the case of D equals 2, and considering finite zero-form symmetry group G, then we define the symmetry category to be the vector omega, which is the category of G-graded finite-dimensional complex vector spaces. So the V can be decomposed into a direct sum of V little g and the little g labeled group element. This is the G grading over here. We also have morphism and associators. And the associators described the phase difference in composing three vector spaces UG, VH, and WK labeled by GHK in two different orders. And this omega, this picture is exactly one-to-one correspond to the F-move picture I showed you before, and the omega is exactly the third group homology element that captures the anomaly information. Also, physically, this VG vector space is interpreted as a defect Hilbert space of an anion line labeled by the group element G. Okay. So that was the symmetry category for finite group. What about the SymTFT? In the short sentence, SymTFT equals the dreamfield center, C of vector omega, which is a modular tensor category with a braiding structure. So vector omega is a fusion category, and now after you take the dreamfield center, becoming a modular tensor category. And we also have the following dictionaries. For instance, the simple anion lines in the SymTFT correspond to the simple object in the dreamfield center, and they are labeled by this the pair where this G bracket G is a conjugacy class, and the pi is a projective representation of a centralizer group G, centralizer group of G by the conjugacy class, twisted by the anomaly omega. And then the linking correlation function of anion lines in the same TFT give rise to modular SNT matrices. The topological discrete boundary condition corresponds to Lagrangian algebra, which means that you just pick a subset or a direct sum of anion lines with mutually trivial braiding. And this is also equivalent to the criterion I said before. Finally, the twist term or anomaly is one-to-one correspond to R omega. Okay, so this works pretty well. There's also list a dictionary over here for the case of the finite group G, which can also be generalized to a general and intrinsically non-invertible categorical symmetry maybe. But for finite group G here we have a very nice equations that are pretty long known in mathematics. Okay, now a central question here is what about the Lie group G? Can we have an analogous picture for this in a category language for our continuous Lie groups? Then we immediately encounter a problem in defining vector omega and Z vector omega, because vector G is a fusion category and the Z vector is a modular tensor category. And in the rigorous mathematical definition, we only allow finitely many simple objects. So if we really want to define a similar thing for the Lie group G, we have to generalize to enlarge our category to allow infinitely many simple objects. So what do we do here? But before proceeding, I'm going to re-emphasize the question is what is the physical situation we are describing using category theory. So for continuous symmetry G, as I mentioned in the beginning of the talk, there are two types of gauging. The first one is the gauging with a non-flat dynamical gauge field. In general, after gauging, you just have a new theory, right? Like QCD or QED instead of free scalars. So in this case, the bulk theory is also not described, it's not a TQFT at all, but is the so-called symmetry series that proposed by Fabio Pruzzi and his students before. Is not the same thing as SymTFT. So if you really want to use SymTFT, we have to use a flat gauging, which is also the central, condition in the first part of this talk. For continuous SymTFT, there have been multiple papers, proposals, starting from the first paper, and more recently also this paper on SymTFT for continuous phase-time symmetry as well. So, and also in our paper, starting from last March, we studied this a case of continuous non-abelian zero-form symmetry with trace BHF TQFT actions, roughly speaking, and we constructed the new thing here. The central thing in our work is that we realized this a UG operator labeled by a group element for non-abelian continuous group G in the bulk. This is a very non-standard thing. We have to use a non-topological operator to really realize something that generates the non-abelian group, not a continuous class. It's not a continuous class. It's a group element here, which would generate the UG operator in the boundary after assigning appropriate boundary conditions. But in this talk, I'm not going to mention this Lagrangian approach, which are just a set of very nice works. But for the time limit, I'm going to be focusing on the categorical part for the next part of the talk. Okay. So this is the central topic of this our paper last September. So the description for symmetry category of a Lie group G we found is this one, the sky tau G, the category of skyscraper sheaves supported on the real Lie group G, which was introduced by Dan Fried, Mike Hopkins, Jacob Lurie, and Konstantin Telemann in a nice paper in 2009. But it's just astonishingly, I think in the physics literature, people didn't really use that or find out this paper, the usefulness of this paper. So what is the sky tau here? The objects are skyscrapers on G with finite support. So roughly speaking, this is the equivalent to attaching different vector spaces to finitely many points on this continuous Lie group G. Also have morphism, but the important thing is lies in the tensor structure. In the monodial structure, to define this, we use a pair of data. The first one is Hermitian line bundle K over G times G, and you also have a symmetry. The first thing, the Hermitian line bundle really defines your tensor product structure between Cx and Cy. So where Cx is the skyscraper sheaves supported on a single point X on G. So X and Y, these are all group elements. Okay. And it generally can be twisted by the Hermitian line bundle K over here. And then the theta is so-called isometry. So basically you can think about over each point on G times G, you have a vector space, a C vector space here. And the theta is a map from 4 different vector spaces to C, which basically can capture the information about your anomaly or the third group homology. Yeah. And this is basically, it's like, similar to your basic intuition, you have 2 different ways to associate Cx, Cy, and Cz. You have 2 different ways. So, then you introduce this big K in 2 different ways, and you say that, then if there's no anomaly, they should be the same. If there is anomaly, you see a phase factor different, the capital to be a little omega. And that piece of information is not, is really lies in the isometry part, theta part. Then a bit technical point is that, okay, So now, this is a little bit mathematical abstract, but you may ask, why do we use this definition of sky tau G? It's just a very simple observation that the nice thing that is what is a tau? The superscript tau here is precisely element of H4BGC. And we all know that, as in the first part of the talk, the H4BGC element, like a tau element, just is perfectly correspond to our physical anomaly polynomials. That's like k times FHF or k times trace FHF is proper normalization factor. And the little k is an integer. When k is equal to 0, then tau is just a trivial element here. It means no anomaly. But when k is non-zero, it means there is an anomaly. Okay. So this is a very good hint that sky tau G may be the correct thing for our purpose. And we also study k for g equal u1 and show how do you really derive the k, the line bundle from the element tau. And the sketch, I'm just going to sketch this derivation. This tau element is 1-to-1 correspond to even bilinear form defined on the lattice. The lattice is a co-character of the U1 Lie group. Basically, well, that's just a home from U1 to U1, in this case, equal to Z. And then we non-uniquely define a bilinear form B based on this even form, this angle product. And from the B, we can just define the bundle K by this action, by this so the twisting. How do we see the twisting action on the C fiber in this way? So here the first line is you can have a action with lattice C times C on the base R times R in this way, but it has a different type of action on the C fiber. And then finally, we just quotient out R times R by the C times C lattice. We get the line bundle defined on U1 times U1 that can be generally non-trivial if tau is non-trivial. Okay. So that's a pretty nice construction. We successfully construct at least a version of the symmetry category for the U1 group. And everything is very clear and precise, and define the line bundle in this precise way. And then another good thing is about the dream field center of sky tau U1, which can be also defined using the lattice language in a nice way in Dan Fried's and collaborators' paper. So, what we found for the case with no anomaly or with anomaly, the little simple objects are pretty different. For instance, if there's no anomaly, then the simple objects are labeled by little g, the U1 group element, and another integers are labeled erep of U1, which is pretty much expected, as a Euro, the B wedge F CMTFT for U1 continuous symmetry, right? You just have two type of anion lines, one generates the U1, another one generates the Z. It is fun, but with anomaly, you have a different thing. And also a very nice observation and matching consistency check in our paper is that we found that we got exactly the same result by pretending that G is a finite group and just apply all the equations when we define the Z of fact G omega. And so with the omega we insert in is this is just a equation that we derived before in the field theory language using the F move. We just use a representative for the H3 group U1 delta U1 with the same expression plug into the formula of the finite groups. We get exactly the same answer. So it seems like everything from different angles, they all converge to the same thing, which means that all the approaches should be correct. And besides that, we can even generalize the notion of model tensor category, although not mathematically rigorous, incorporate infinitely many simple objects in the dream field center. In this way, you can even define some continuously infinite dimensional SNT modular matrices, which is, I think, maybe awkward thing for mathematicians, but for physicists, this is really nothing strange. We can use some delta function and define these infinite dimensional matrices similar to operators in quantum mechanics. Say you quantize things on the line in a coordinate basis, it's a similar thing like that. Okay. And the ST matrix also satisfy the SL2Z generator relations in this nice way. Okay. And then with this topological annealing lines, we can also discuss the topological boundary conditions with or without anomaly. And for instance, there are boundary conditions corresponding to having a full U1 symmetry, or the one correspond to gauging a non-anomalous ZQ subgroup of U1. It's all consistent with our physical intuition. But strictly speaking, these are not the honest Lagrangian algebra in the old definition of Lagrangian algebra. Because as a reminder, when you define Lagrangian algebra is in this model tensor category, the Lagrangian algebra has to be itself has to be an object in your the dream field center category. However, in this definition, they do not allow this infinite direct sum of simple object. So to really define the Lagrangian algebra for the Lie group, we have to enlarge, just to enlarge the category to have an even larger category. It is part of ongoing work. So
Sorry,
I'm
I
going to
don't
also
understand. So
yeah,
can you go
yeah,
back for a second? So
yeah.
this just needs to form an algebra. Are you saying that even in the sort of mathematical definition, these things wouldn't actually, this infinite number of objects wouldn't form an algebra object?
Yeah. So in the math definition of either fusion
It is
well,
allowed.
in the fusion category of model tensor category, this Lagrangian algebra has to be an object in that category. For
Right.
all the cases of finite, finite groups and finite categories.
Right.
However, yeah, the problem is that in this definition of a sky category, the objects are scatter sheets with finite support. It only attach vector space to finitely many points G on G. So you cannot define an object such that you attach a vector space to all the points on the U1. You imagine these things like you attach a vector space to every point on U1, so you have a continuous infinite dimensional vector space like that.
So, but if you think
Yeah,
of
so
it in terms of module categories, right? If you think of the symmetry, and I think for you it's 1 plus 1D, is there a
yeah.
notion that there's a module category that would correspond to changing this boundary condition from, say, Dirichlet to Neumann or something?
Well, mathematically, the module category, I think it's always pretty hard to prove rigorously. So from mathematician standard, I can't say about that. Yeah.
They don't discuss module categories.
I'm not. Yeah. But for physicists,
Yeah, sure. We can
I
always
think we
go
don't
to
care
the
about that. We don't care about that.
No
Yeah,
problem.
if dimensional Hilbert, like Hilbert space is totally fine. Yeah, let's say you just have quantum mechanics on a line, so something like that. But even in that case, strictly speaking, you use the fundamental algebra. So yeah, so there should be different approaches to really rigorize this notion of a infinite direct sum, like fundamental algebra, for instance.
Okay, thanks.
Okay, yeah. Then I'm going to just briefly mention SU2K without giving the equations in the paper. And so they basically largely uncharted territory still for non-abelian Lie groups. But we just pretend that the formula for finite group can be used, and we can derive something like ST matrices. But like none of these are a really rigorous thing up to now. And also for the SU2 case, you may ask what is the representative for the third group homology? And I think in that answer, nobody has studied that before. Yeah, it's just a purely algebraic question, but even that, nobody has studied that before. So as a summary, I think for the continuous Lie group, even for continuous Lie group, is still a huge playground for people to work, both for mathematicians to develop things more rigorously, or just physically you try to compute things. For instance, what are the modular matrices for non-abelian group G with anomaly, and there are tons of questions like that to study. And also, which is a proper generalization of this guy tau G to incorporate this infinite direct sum. So in our paper, we propose that maybe you can use the quasi-coherent sheaves, but the quasi-coherent sheaves, generally speaking, only work for the algebraic groups like SL2C, complex groups. So and also you may wonder about what is the hard dimensional generalization. So there's the n vec G omega for continuous symmetry with the analogous notion. And so there's a paper by Stockel and Matt Yu, and just recently, and they also use the QC quasi-coherent sheaf formulation, and that we proposed. But I just think that still, if you want to be mathematically rigorous, that only apply to algebraic groups probably. Yeah. And so I think there are still tons of open questions, and most of questions are still open. And also, what are the continuous intrinsically non-invertible symmetries, as say the cosine theta symmetry or something proposed by people more recently. And there so in general, I think all these questions are pretty unclear and all up to future research. So thank you very much. That's my talk.
Hey, thanks a lot for a nice talk. Are there more questions?
I have a question. You talked about perturbative anomalies, for instance, how to realize them
Yes,
as
yes, the
F-moves.
perturbative anomaly. Yes, yes.
But
These are all perturbative anomalies.
yeah, but sometimes there can be also non-perturbative anomalies. For instance, there is the Witten anomaly for SU2. Do you know how
Yeah,
to
yes,
get
yes.
it
Yeah,
in this?
yeah, yes, very nice question. Yeah, yes, yeah. That's a very nice question. So, yeah, this FHF only capture perturbative anomalies. And the Witten anomalies, yeah, we don't think it can be captured by the tomorrow defect network. It's just a different thing.
I
It's
see.
it's like in general in the class of eta invariants that can be captured by this index of Dirac operators. That stuff. It's generalized to the general type of eta invariant anomalies. And the short answer is no.
So it's not captured by flat background fields. You really need to introduce non-flat backgrounds.
So yeah, that's that I'm not sure, because I think the flat background gauge field is still a good model of a general anomaly for continuous groups. But I'm just saying that it's probably not the F move, not captured by F move.
But any flat background can be captured by topological defect network. So if you can realize the anomaly only in terms of flat background fields, I would say that then you should be able to reduce by some F move. Because an F move is the most general gauge transformation that you can do on a flat background.
Yeah, that I can't say for sure.
Okay. Thanks.
Yeah, for continuous group, I think you be careful. Yeah, it's just a subtle thing. But yeah, I don't have any definite comment on that point.
Any other questions? Okay, I don't see anyone else, so let's thank Yinan again.